All right, good morning, everybody. Thanks for tuning in. Today, we're very excited to have Professor Alejandra Castro from Cambridge. She's going to tell us about gravitational perturbations near to extreme Kerr. Please take it away.
Okay, thank you. Thank you for the invitation. Thank you for joining in early in the morning. Today, what I want to do, I'm going to be talking about some old work upon request of Dan that he explicitly said that he wanted to hear about the Kerr black hole. So here we go. We're going to talk about the Kerr black hole. But I know that the audience is pretty broad. That's my understanding. So if there's aspects of what I'm saying that are not very clear, please interrupt me, ask me questions. Also, there are various portions that I'm not going to give a lot of details, but if you wanted to know more details, because there's a lot of many moving pieces in this discussion, just interrupt me, tell me, and I can give you a bit more details on what's going on. So just feel free to interrupt me at any point. I know that in Zoom tends to be a little bit more difficult. But in any case, let's get started. So we're going to talk about gravitational perturbations. And from my perspective, as someone in the high energy theory community, for me, studying perturbations of black holes is something important because I want to understand the inner workings of a black hole. And the basic way we do this, and as a physicist, as a theoretical physicist, or even as an experimentalist, if you have a system that you want to understand, the basic thing that you do is that you perturb it, right? You throw little things at it and you see how it responds back. This is the most elementary way that we have to understand how a system behaves and how it works. And from my point of view, the reason I'm interested in asking about perturbations around a given black hole background is because I want to understand aspects of its quantum nature. In particular, I want to understand what can I learn about the spectrum of the black hole that could be something very interesting. And also from this quantum perspective of understanding how the black hole works, I want to understand what are possibly constraints, or like how can I build an effective description of that system, and what are ingredients that I have to keep in mind, and how various aspects are constrained by it. So in that context, of building some holographic description of the black hole and understanding how it works, there's three questions that come about a lot. And so one of them is basically, what are universal properties of a description of a black hole? So we know black holes are very robust. There's many laws that we like to describe about them. And so you might want to understand, okay, what are things that all black holes share? And what are those things, and how do we describe them in a holographic setup? But there's also things that we expect in that description that depend on the background. So basically on parameters that the black hole relies on. It could be its mass, its angular momentum, its charge. Those are things that are inherent to the black hole. And then there's also things that might depend on the surrounding of the black hole. Okay, so in which theory do you have the black hole? And in the context of this talk, perhaps something concrete to think about is like, is the black hole embedded in Minkowski versus in ADS? How should I adapt this inner workings? How should I adapt this quantum description of the black hole, depending on which the sign of the cosmological constant or not? Or should we always think of black holes on just one single bucket and not make these distinctions? So these are the types of things that I have in the back of my mind as we're trying to probe black holes. Now, the way that we're going to do this, so an interesting approach to understanding the nature of black holes comes by looking at basically how extremal black holes behave, or near extremal black holes behave, and then notice that in those situations you have either an ADS2 or a near ADS2 near horizon geometry. And this has been used quite a lot, and it's an advantageous approach because in this context, when I write down the word ADS2, or at least for my mind, immediately pops out, I can use some tools of holography to understand what's going on, some tools of ADS CFT to describe this. So this is something that we find very rich and advantageous in order to make progress in our understanding of black holes, of both the classical and quantum aspects of black holes. So I want to say in this context, so anytime you have also just moving a little bit away from perhaps holography if you wish, but in any case, anytime you have this ADS2 or this near ADS2 factor, it's a case where as a theorist, you should also, even if you don't care too much about ADS CFT or some holographic correspondence, it's a case as a theorist that is telling you you have an enhancement of symmetries. Okay, so you will have more tools and knobs at your control to quantify what is the physics that is happening. That I'll elaborate more. And one of the things that I also want to, that I'll review as we go through the seminar is that this concept of near ADS2, which is basically the backreaction of the black hole, also has a lot of interesting structure that is universal. And so that is something that we want to exploit as well. Now, I should also say that ADS2 from the context of ADS CFT is one of the most enigmatic cases of ADS CFT. So there's always conservation of difficulty as well from this theoretical perspective. So we will have a lot of symmetries that we will gain and that will give us a lot of nice things about how we organize quantities. But from this quantum perspective, there's also some things that are less understood in comparison with higher dimensional instances of ADS-CFT. But don't worry, this part, this enigmatic part, I mention it for completeness. It will not pop up in the talk. If you have questions about this, we can talk about it more through the questions. But okay. So what I want to do today, so basically the punchline of today is that I want to understand how these developments, how these lessons from the past adapt to the Kerr black hole, the four-dimensional Kerr black hole, the solution to the vacuum Einstein equations, okay? And so three things are going to happen to you, roughly speaking. We're going to revisit the spectrum of axisymmetric perturbations around the black hole. We're basically going to see how some of these universal aspects that are generic in some other more simple cases also apply here. And one of the parts that will be important is that I want to translate those statements into what's known as the Tsiolkovsky formalism to describe gravitational perturbations. And many of the things that I'm going to tell you, they will look very similar to what happens to simpler types of black holes, but there's some unexpected twists and glues that we thought that were interesting. And so we'll see here how you react to this or don't react. So what I'll be telling you today, it's based on this paper that is from 2 years ago. That has 4 collaborators with them. So Victor Godet, Joan Simon, Wei Song, and Boyang Liu. And I should say that if you find the equations pretty, or maybe not, or if you find like, oh, this is a nice compact way how to describe what's happening, I should put all the glory and all the praise on Victor and Boyang because they're really behind the hard work of like making a formalism that is quite complicated and intricate, simple, and basically understand in nice terms what's going on. So they're really like at the heart of all of these computations. So in any case, so with that said, basically what's going to happen next, there will be 3 sections. So I'll review this concept of what is so nice and powerful about ADS2, near ADS2, and this concept that I described as JT gravity. So I'll tell you what I meant there that I mentioned already very briefly in the introduction. So we'll make the precise statements there. And then the main part of the talk is basically understanding where the Kerr black hole stands in that context. So where's this JT sector that has made a lot of noise in other contexts. And then we'll finish with some conclusions and some outlooks, okay? So this is how we'll go. Any questions so far? I know I've just been basically waving my hands quite a bit, and now we'll start writing some more equations. Okay, so let's get going. Okay, so let's talk about ADS2 and near ADS2 and this concept of JT gravity. So imagine you have a black hole that we'll call non-extremal. Here, I've drawn the Penrose diagram of basically something that is like the Rice-Nostrum black hole. But what I want to emphasize here is that basically, if you have a non-extremal black hole, generically, the characteristic is that you have an outer horizon and an inner horizon. You can see my pointer, right? Yes, okay. So you have basically an inner and an outer horizon, and this region 1 is basically being outside of the black hole, and this part here is the very far region of the black hole. Okay, so in this context, an extremal black hole is basically defined as the confluence of the inner and the outer horizon. So you're bringing these two horizons closer together. And the endpoint of that is basically this resulting Penrose diagram, where this region here shaded in blue with the red stripies here, well, it repeats each other, but basically this region here is this region of ADS2. So this is what we call this near horizon region for the black hole. And then there's another part of the geometry that is still asymptotically flat out here. Okay, so this is how the Penrose diagram of an extremal black hole looks like. And as I was telling you before, there's quite a lot of nice things that happen when you have this extremal limit. So as a definition, it's basically the confluence of the outer and the inner horizon. When you are at this point, the Hawking temperature or the surface gravity of the horizon is exactly 0. As we've been talking about, you have an enhancement of symmetries and go basically from just having a Rindler type geometry near the horizon to having an ADS2. If you wish, in certain contexts, depending on the parameters and the embedding, you can even have more symmetries. You can make the black hole supersymmetric if you wish. This is not going to enter in the discussion today, but it's an extra plus if you want in these constructions. And another important thing to say is that the area of the horizon in this limit, so when you take r plus equal to r minus, is still finite and it's huge. And so from the thermodynamic point of view, it means that you have a huge amount of entropy. Now, this picture, I mostly won't be drawing the picture like this. Just to visualize it a little bit better, I'll be drawing basically this picture in this way. So here I have this throat, this ADS2 throat here. It is somewhere here in the bottom. And then you have some asymptotic structure at infinity, like basically this point here that for this talk, it will be asymptotically flat, but some of the things that I will say will also apply if the black hole is asymptotically ADS4. Okay, so this is roughly like the picture that I'll draw how I'll visualize this. Now, this part, if you're only in the ADS2 part, and this is all that we do in life, this is still, it's a quite interesting region in 2B. So if you wanted to understand, for instance, aspects of the entropy of the black hole, so here I've written down the Bekenstein-Hawking entropy, and you wanted to understand it in a statistical way as basically counting some number of microstates, the fact that you have this ADS2 region gives you a lot of power and a lot of control. A lot of the successes, for instance, in a string theory setup to understanding the origin and how the computations go and how can you match quantities to give it a microscopic description relies a lot on this. Okay, so just if you wanted to just stay in this very extremal case, it's a quite rich case to stay in. But that's not what we're going to do today. Today, what I want to do, I want to go a bit away from extremality. Okay, so I want to kick the black hole and see how it back reacts. So let's first consider a simple situation where I'm going to have basically a spherical symmetric configuration. And here I've drawn the geometry in 3 steps. So basically you will have the full geometry that describes the entire space-time, and then there will be a region in where you will have your ADS2 times S2 geometry, and that's what I'm describing here. So you will have the sphere with a constant size. And then this part where I have G of 0 is basically some metric in ADS2 that I'll make explicit in a moment. And what we want to do is we basically want to understand how do you interpolate between the two of them, okay? So you might imagine that when you kick a bit away from this point where this is constant and this will have a non-trivial profile, you can view it as like adding some deformation to it. Okay, so let's do it for the case of Rice-Nostrum just to see how the equations look like. So this equation that I'm writing here, this is the line element where I have some mass and some charge, and I'm going to take this extremal limit of m equal to q for Rice-Nostrum. And to get down to the bottom, so to get down to this metric here, you basically do a coordinate transformation where you basically redefine your radial variable as something that is the location of the horizon plus lambda times a new coordinate set, and you rescale time. And what you do to get from the whole geometry down to something in the bottom is taking lambda going to 0. And you can see from here that if lambda goes to 0, you're going close to the horizon, like your original radial variable is getting close to R0, okay? And lambda in that context is usually called a decoupling parameter in some sense, because it takes you from something like that was very far. If you take that parameter to 0, you get to some other geometry that is finite. This geometry doesn't depend on lambda anymore, and it kind of forgets about the rest. So that's also why you can also understand why you have this infinite throat. Okay, so this is how you go from the top to the bottom. That's your ADS2 times S2 in your horizon geometry. Now, in describing the middle, basically, what is this field Y here that you have sticking around? In a very simple situation here, I'm ignoring, there's also a backreaction from the metric of this side here, but it's not going to be important. But basically, the only thing that you have to do is that in this coordinate transformation, keep the next term in lambda, okay? So for a static configuration where you don't have any time dependence, what I'm describing by this field here, Y, is basically this term, okay? So it's changing the size of the sphere, okay? So it doesn't look very fancy or complicated from that perspective. That's all that is happening in this setup. But okay. But that's not the end of the story. The actual fact is that this part of the theory, so we want to actually make it dynamical. So it's not just about like keeping an extra term in a very static decoupling limit. So what has been shown is that this portion of the dynamics, so when you move a little bit away from this near horizon geometry, the dynamics of the system is very well encapsulated by a two-dimensional theory of gravity. So originally everything is in 4 dimensions, but you can, for instance, if you're more comfortable, you can do a dimensional reduction of your 4D theory, or it can also be argued just from symmetry principles or from the equations of motions, that your effective action, basically everything that you wanted to know in this portion of the geometry, or many things that you wanted to know, is basically described by this very, very simple action in 2 dimensions. This is what we call JT gravity, okay? So it's basically here, you have this field Y that multiplies an Einstein-Hilbert term, where here you have the curvature tensor, the Ricci scalar, and a negative cosmological constant, where this curvature is basically the curvature of this 2D space, okay? And so then in terms of the equations of motions, the dynamics of this field, so there will be 2 equations of motions. One, if you vary with respect to Y, it will tell you that the curvature is always negative. And so then here you have your ADS2 part. And then if you vary with respect to the metric, then you get hit on the Y field, and it gives you an equation of motion for Y. Okay, so this is the typical equation of motion for the scalar in this model of Jakiv-Teitelbaum gravity. And something that I want you to remember, this is a bit of the ADS-CFT jargon. This field basically will have an effective mass which is mass squared equal to 2 in ADS 2 units. And in terms of the conformal dimension that we like to define in the context of ADS CFT is a field of conformal dimension equal to 2. Okay. So this is JT gravity. Okay, so if you ever hear another talk again on JT gravity, this is the theory that they're describing. Now, why is there so much fuss about this theory? It's a very simple theory. It has very, very, very few ingredients. Well, this theory actually is believed to be quite universal, to be something that will be describing this back reaction if you move away from ADS2 to near ADS2. And basically everything dynamical about this theory can be said in terms of basically Goldstone modes that live at the boundary, which is a Schwarzschild effective action for these modes. In the context of the black holes and the thermodynamics, this portion of the theory is what tells you how the entropy of the black hole is going to react when you go from 0 temperature to some finite amount of temperature. So this is the first leading correction to the Bekenstein-Hawking entropy away from extremality. And also one of the things that was very nice about this theory, because then if you look at correlation functions and other observables, many of them are shared by a dual theory, which is this SYK model that I won't go into, but just for the context of its bus in ADS CFT. Okay, so
why is like a dilaton?
Because it multiplies the Ricci scalar.
Yeah, so it's like a dilaton.
Yeah.
And in this story, it's part of your S2 or
What's that? Yeah, it's basically it's the size of the. So when you do that, you can see it from the dimensional reduction. So basically, Y is controlling the determinant of the 4D metric.
Hmm.
And so then that's why it sits in front here. And so that's, yeah.
So it's, should we think about this as the JT embedded in this new horizon?
Yeah, exactly.
Because in JT, we don't talk, people don't talk about S2, right?
No, right. So here I'm freezing the S2 for this talk, and also in this case, like that is adequate for the Rice and Ostrom, is not doing anything. You can of course turn on modes on the S2, add deformations here. And that's also why I'm writing ... So depending on like what came from your higher dimensional like theory, you will have other terms. And also this is an expansion near to this ADS2 point. So, but the part that is really controlling everything like thermodynamical about the black hole at this stage, the claim is that this is all you need to know, that everything else, at least a leading order, the first effect when you turn on the temperature is basically just given by this action.
I see.
That's a claim.
And I have another question. You call it a near extremal, but what you describe is expanding around the near horizon region. Is it the same thing?
Well, it's doing those two things at the same time. So yeah, because ADS2 is very fragile. So anytime that you put a finite energy excitation on ADS2 itself, you will break it. Okay, so this is so in some sense when you add energy. So if you wanted to say something if the ADS2 is T equal to 0 and you wanted to say something at finite temperature, you have to add some energy so that it makes sense to say that, oh, you're finite temperature.
But the condition that M is equal to Q in the previous slide is still...
Oh, I was just doing it exactly. Yeah, so there's two things that you can, so there's two things going on. So you can also move so there's two steps that you can do. And actually, Achilles knows this also very well. So there's two things that you can do. So you can turn on this, depending on how you pick the profile of this Y, which solution you pick, you can basically make the mass of the black hole change. That's one thing that you can do, but you can also modify this Y in such a way that it's just reconstructing for you the extremal black hole. So it's doing something a little bit more boring. So that's what I was illustrating in the previous slide. I was illustrating the boring thing that the Y can do, just so you have some intuition about where it comes about. But I could have written in that previous slide something I'm also turning on the temperature of the black hole, but it's a little bit too many equations to illustrate the point. But I could also have shown you how this middle line looks like if you also have like the deviation away from this exact equality.
No, these two things are.
It's basically the same effective theory that is describing it. So JT gravity is doing both for you. So it's just choices and the JT description. So it's not a different theory. So for both of these things that I'm describing, either you just want to go up in the radial direction without changing the mass of the black hole, or if you want to go up in the radial direction while changing the mass of the black hole, these are both things that are described by this JT effective action.
Thank you.
And the simple cases that we're describing right now, and the spherical symmetric cases. Any other questions?
Yeah, maybe I want just to emphasize that the boring thing is always necessary. Like, because this ADS2 is very fragile, you can't do, even if you want to just add a little bit of energy to go away from extremality, you can't do just that. You still have to do the boring thing and climb out the slope. Exactly.
So like, and this is the enigmatic part that I was talking about ADS2, the fragility that it has, that anything, that's why it's difficult to understand it in some sense, because most of the things that you want to do, most of your experiments will force you to go away from this ADS2.
But the two things are equivalent in the sense that there is some change of variables, or that we can translate one to each other, or two different things that you can do.
Sorry, which things that you can do? Just moving
away
from
to go away from m equal to q.
It's all described by this action. So it's choices inside of this action.
But there are two things that we can do, right? To change the extremality condition, m equal to q, and to go away from the near horizon.
Oh, but if you change m and q, you will have to move away from the throat.
Yeah. So
you can't change m and q without really like, so what this new perspective is telling you is that if you wanted to deviate away from any m equal q, you have to like move outside of the throat as well.
Is it equivalent to not changing m?
No, it's not equivalent. This is a different, okay, so there's different choices of like, so basically just on the technical side, this is an equation that has three components, and roughly speaking, it will have three solutions. So depending on how you pick your solutions, it's what its interpretation is going to be.
I see.
That's a short version of like the answer to this. Yeah. And there's an excellent paper of Achilles and collaborators that explains this in detail for the Rice and Ostrom case. So okay, so where was I? Yeah, so these are parts of this action that are quite interesting, but now I really want you to remember, like, this is the thing that you kind of have to memorize for this talk, that this box equation delta equal to 2. So just remember this. I know it's a lot to ask for people to remember things, but just one thing, remember delta equal to 2 is a very important thing, which is basically related to the mass of this field. And then the last thing that I wanted to say, which is also kind of a cute relationship about how y also is related to the geometry, is that, so this ADS2 geometry has 3 killing vectors. And basically, you can write these killing vectors. Each of these 3 killing vectors can be associated to one of the 3 solutions that you have for y. So there's a very nice compact way how you can write down the killing vectors of SL2, which is written in this form. Okay, so it's basically the derivative, the divergence of y. Well, not the divergence, the curl of y basically gives you each of the 3 killing vectors. Okay. So that's very nice. Okay, let's move on. So now let's try to put all of this mess inside of the Kerr solution. So here's the Kerr black hole. So I I tend to, if I was giving this talk in a Blackboard, I would never write down this metric. I would just tell you, remember it by heart. What is a Kerr line element? But okay, we're doing slides. And so then I can write down the line element to tell you that looks very messy. That's all my intent of writing down this line element and putting some definitions of the various functions that enter here. This is a complicated line element. I admire Kerr for finding this as a solution to the Einstein's equations. I don't think I would have been capable of noticing that, well, without, now we have Mathematica, I guess it's easy to check that it's a solution, but this is quite impressive. It's a very complicated solution with a lot of angular and radial dependence. And so everything that I was saying before, I had a nice, perfectly round metric, a sphere. And so then here you might say, oof, how are you going to make the parallel between the things that you were saying for Royce-Nostrum for the Kerr solution? But there's some things that are shared. So let's first highlight some things that are similar for the Kerr solution compared to our Royce-Nostrum black hole. So the first thing is that I can also take an extremal limit. So in the conventions for the angular momentum and the mass of the black hole, this is how the extremal limit looks like in this case. And then you will do a coordinate transformation that is very, very, very similar to the one that we did before. So you just shift R to the by this way, exactly the same as we did for the Royce-Nostrum. You also rescale time. And the only thing that perhaps is new that we didn't have in the Royce-Nostrum is that we have to shift the angle around. Any case, the point is that you get a resulting, as you take the limit lambda going to 0, you're going to get a line element that out of this that is regular, it's finite. And this is what people call NEC, the near horizon of extremal Kerr. And what we want to highlight in this line element is that we basically, in this line element, we have a portion that is the ADS2 portion. So very similar to what happened in the Royce-Nostrum case. So here's where the ADS2 lies, but there's some differences basically that I don't have it times a sphere. Okay, so you have basically here a fiber on the phi direction, and then there's the other angular dependence that is giving you some warping factors in front of different portions of the geometry. So when you ask me now, how do I think about this Y field as like deforming the sphere? This is the part that is like, yikes. It's a little bit more complicated, it feels like. And so what I want to do in the rest of this part is basically trying to demonstrate how do you see this Y deformation in this beautiful mess. Okay, so we'll try to understand where the Y field comes in. So very good. So we decided to do it in the following way. So we're going to write down here, again, I just wrote down NEC. Okay, so it's the same line element that we had before. So this is basically going to be the metric of ADS2. And this is the fiber here. The way that we did things was basically in a covariant way. So I don't need to write down specific coordinates for the ADS2. And this is where Victor and Boyang were great. They basically deducted everything in a very covariant formalism. So pick your favorite coordinates for ADS2 and every equation will go through. So if you see this xi's are basically coordinates on ADS2 and this AI is a gauge field. You can interpret it as a gauge field on ADS2. Okay. Now, with some foresight that I'll explain to you in a moment, let's first just say, okay, let me add a perturbation, okay? And this is not usually how we do things in general relativity. We don't like make guesses on which components of the metric we should deform, but I'll tell you that this will be consistent in a moment. But let's just imagine that you're deforming the metric in this way by these fields placed in these positions, where the fields, and this is the part that I'm taking as axisymmetric. So I'm making them depend on these 2D variables and theta, but I'm not adding any phi dependence in the perturbations. Okay, so one thing that you can check, you expand in this parameter epsilon and look at what happens to the Einstein's equations in vacuum at linear order in epsilon. And you will find that you basically have, well, the first statement is that this field B is basically determined by chi, so you can forget about it from now on. And then there's a second order differential equation, partial differential equation for x, where this is the Laplacian on this ADS2, and then there's some angular part for the differential operator. Okay, so this is what you get from plugging this ansatz and expanding into the Einstein's equations and expanding to linear order in epsilon. Now, why did we decide to do something like this? It's because we could see what the imprint on the metric was right away. So we could see like, oh, how would the metric react? And it's a consistent thing to do, at least locally and linearly in the equations. This was a perfectly fine thing to do. Now, the disadvantage is that usually when you talk about metric perturbations, you never use this form, like you never do this. And so it's like, what's going on here? Is this a gauge redundant thing? Like you're not mudding up at diffeomorphisms. Like what is the physics that's going on? How should I interpret this? In contrast to the usual way that we think about basically gravitational perturbations. So our task then was like, okay, so let's put this in the usual formalism of Tolkowski, which uses a Newman-Penrose decomposition for the gravitational modes.
Can we just ask why not just keep the order lambda terms in the near extremal limit the way that you did for Reisner Nordstrom?
Here we did wanted to make a distinction that there's two things that you can do. Because you can deform the black hole, not necessarily in the same way that you do the decoupling limit. So you could equate epsilon with lambda, but you don't have to at this stage.
Okay.
It's not necessary. So because you can also just have perturbations be perturbations without them being associated to the fact that you decouple the geometry. So that's why I'm introducing this epsilon symbol as being a bit different. But of course, you have it is consistent as we get to the JT sector to say, oh, we can make epsilon be equal to lambda and then see how it relates to the decoupling process as well. But conceptually, like a priori, they're two independent, you can talk about gravitational perturbations without having to have the need of a decoupling limit.
Yeah, so is it the most general axisymmetric metric perturbation?
Well, let's go through that. So this is
or there is a choice, there is a choice of some.
This was part of what we wanted to show. So we'll get that in a couple of slides. I'll tell you about that. Okay, so the first thing to say is basically, so usually when you write down gravitational perturbations, you use the Weil scalars basically the two helicities of the graviton are encoded by basically these two contractions of the Weil scalar. So here C is the Weil scalar, and they're contracted against some tetrads defined on the Kerr background. And this is basically the formalism that you use. This is what encodes for you the gravitational perturbations of the metric, okay? This phi0 and this phi4. And so, okay, so first let's just try to understand a little bit like how are these things related. So we have this background, and so then you can easily compute the Weil scalar for this background at linear order in epsilon. And basically what you find is these two expressions. So phi0 here is basically two derivatives of this field chi with L, and phi4 is again two derivatives of chi against this field N, where N and L are basically vectors defined on this ADS2 that are null, and its inner product is -1. Okay. So there's clearly a relationship between these two fields. And in some sense, at this stage, something that you can see what's going on is basically that we decided to relate a scalar degree of freedom. So chi basically behaved, it's a scalar field, and to construct a spin 2 perturbation, you hit it with two derivatives. And then since you have two helicity states, depending on how you contract those derivatives, then you get the +2 and the -2 helicity mode, okay? So you're just trading basically at this stage, it looks like you're trading a spin 2 degree of freedom by a scalar degree of freedom. Okay. Now, let's decompose this furthermore, as was being asked. So let's look at what are called usually the propagating modes. So how do you relate this to the usual solutions to the Tolkowski equation? So the equation that I showed you that chi satisfied was this one, okay? So you can build solutions to this equation, which it's not difficult. You can write a separable ansatz in terms of like a function of theta times a function of the ADS2 coordinates. And the solutions that usually you consider are solutions where this functions, it's basically this part of the wave equation is it's a hypergeometric, like the differential equation for the angular part, and its solutions are going to be Legendre polynomials. Regular solutions are going to be Legendre polynomials. And then the ADS2 part is basically just going to look like this. Now, the fact that I wrote down here Legendre polynomials puts a restriction also on what the value of L is. So L has to be bigger or greater than 2. That makes the solutions well supported on the sphere. In particular, they don't vanish at 0 and pi. And then the conformal dimensions. In the language of like, okay, how do you interpret each of these fields in the language of ADS-CFT? They will have conformal dimension L plus 1. Okay. Now, in relationship to the Tolkowski formalism, so if you go back here in the Tolkowski formalism, you would have, I just wrote one of the scalars for simplicity, it works for both. You would have decomposed the Weil scalar as well. You write down a separable ansatz, and the angular function will be exactly the same as this angular function. And then you can show that this ADS2 part of the Weil scalar has an equation of motion that you can read in Tolkowski's papers, and it's basically the same equation of motion that you get for chi upon this identification. So
sorry,
yes.
Can I ask you one thing? So here you say that the conformal dimension is to be greater or equal than 3. So this sector doesn't include the dilaton.
Yeah.
Okay.
That was my next comment.
Okay.
Yeah. So if I look at the propagating degrees of freedom, yeah, as Chiara very nicely remember, I was looking for something that had delta equal to 2. It's not here.
It's not here. Okay. Where is that?
Okay. So you might think, oh, you went through all of this and you didn't get the JT sector. I guess now we can hang up and go on our merry way. No, there's a little bit more to say. So sorry, I'm a sarcastic person. In any case, so this guy, so if you impose that you want your solutions to be single valued on the sphere, on this angular variable, then everything will have delta equal to 3. And so if you look at any like gravitational perturbation that is discussed in the literature generically, if you open your Chandrasekhar book, if you go and read the papers of Tolkowski, the JT sector is nowhere to be found. It's not there. But okay, but this does address that this ansatz does contain all of the propagating modes. So the infinite tower of axisymmetric propagating modes is basically described by this. So where is the JT sector?
Sorry, can I ask you to clarify? So what are you telling us? So can I just put one of those axisymmetric delta greater than or equal to 3 modes on ADS2 and leave it like that? Will that be consistent, or is this
it's
still
part of the gravitational perturbations? That's all I'm saying. This is a linearized analysis, so I'm just telling you, like, right. if you linearize the graviton around neck, these are modes that are going to be there, like. That's all the statement. I'm just making a statement about how the linearized Einstein's equations behave.
Right. Well, but what I'm asking is, so ADS2 was fragile in the exactly spherical symmetric case to any perturbation that had any energy. This certainly carries some energy. So if I
but they're all irrelevant.
So those on ADS2.
Exactly.
Is it still going to require me to break away from ADS2?
In some sense, like if you turn these on, these are irrelevant operators. So even from the language of ADS-CFT, you have a tower of irrelevant operators. And if you turn them on, then they're going to make the theory flow. So yes, they break your conformal invariance in that sense. The thing is that it's not the JT sector, which people attribute that sector in particular to be the one responsible for the entropy and this chaotic behavior that is like tied to the Schwarzschild action. So if you were hoping to tie with that, to explain why the entropy of the black hole is increasing, it's not going to be tied to these modes. That's all. But yeah, as you say, like these things, like if you turn them on and you see, okay, what is happening here, like yeah, they will make you like flow like away from the neck point of view.
Good, thanks.
Yeah. But okay, so, but let's revisit again this equation, and let me, in some sense, weaken some of the restrictions that we usually impose. So usually the story was that when you looked at these solutions, you wanted Legendre polynomials, right? So that they did not blow up at 0 and pi. But this equation, this differential equation, will also admit locally solutions that will be Legendre functions. Okay. Then they're going to be singular from the point of view of theta. So they will either have a singularity at 0 or pi. And so what I'll ask you to do is to consider the range of these solutions when you have here that they can go down to 0 or 1. Okay. And in this context, then the equations of motions, they all behave the same. And the chi here, this radial part of this ADS2 part of chi will have the same Klein-Gordon equation. But now you can notice, because I lowered the value of L, you can have it to be 1 or 2. Okay. Now, what I'm going to be using as jargon, so what, and I will try to convince you of this. So this L equal to 1 mode, which will have conformal dimension equal to 2, will be part of what we'll describe as the JT sector. And then there's also a marginal mode, L equal to 0, that I will probably, I will definitely not have time to discuss. I'm getting close to the hour. But if you have questions, this is quite interesting in terms of deformations. They can have 3 different types of effects, but like if you're interested in symmetrics or top knot effects on the exterior, or just changing, the simplest change that this does is changing the value of J also as a marginal mode. There's something very rich to say here. And we discussed what happens in the L equal to 0 case in our paper, but for completeness, let me focus on this. Now here I also wrote down the solutions, so this Legendre functions, and as you can see here, they're 1 over sine, and so you're like, yikes. And then this is the part where they're not with full support on the sphere. Okay, so very good. Now, why would you ever do this? Tolkowski didn't do this. Why? This sounds like a terrible idea. It sounds horrible. Who would have thought of this? Okay, let me insist for a moment. So let's just like have a little bit of open-mindedness and say, okay, let this woman consider these singular modes for 2 seconds. And so let's look at this L equal to 1 mode. Okay, so and here we picked the solution for the singular part. Now, we don't like it because it's ill-defined. And so if you look at the Weil scalars, okay, the solutions to this is not going to give you a 0 Weil scalar, but I will insist that the 2 Weil scalars that I had when evaluated on this modes are 0. So you first want to cure the fact that the Weil scalars were blowing up on your face. And basically it's because of this, this extra 1 over sine squared that you have down here. So the chi itself doesn't have a problem. So that sign divides that sign. And so it looks, naively, it looks fine. But then the Weil scalar has an additional 1 over sine squared. And so that's where you would see the singularity from the Weil scalar's point of view. And so we don't want that. So we impose this as a condition. We want these things equal to 0. Now, the fun part is that if you then say, okay, that was the equation of motion for it, and then I have 2 equations that make the Weil scalar 0, and then you impose it, you combine these 3 requirements, it gives you that equation. So this is an identity that you can check. It's not difficult. Actually, it's easier to go from here to there, but basically this equation is equivalent to those three conditions. And I hope you remember this as recognizing it as the equation of motion that you got in JT gravity. So that's great. That's a very nice, promising result.
But what about the other wild scalars?
There's only two.
The rest vanish regardless.
Yeah, the rest you don't have to worry about. They're just, if these two are zero, then everything else is going to go through.
So if all the wild scalars vanish, then it means that
we're not there yet. So we made the Weyl scalars vanish, but I'm not making the field trivial. So of course, one way that you can make the Weyl scalars vanish is say, oh, just make that mode zero, right? But I want to still keep it on. So this guy will still have an effect on the metric.
but you're not changing the curvature.
No, it's not. It's not going to be propagating in the usual way, which is fine because also this is also, even from the JT point of view, this is a constrained scalar. It's not really a propagating degree of freedom. But the whole point is that I don't want to turn this off, right? So I don't want to say, this whole thing is zero, right? So I want to still say, no, actually just impose this equation of motion, and then the Weyl scalars will be fine. So, okay. And from that side, then you have to revisit again the metric and say, okay, look again at the metric, and now you have this field satisfying these equations. And one of the things that you'll notice is that, okay, the Weyl scalars are trivial, but this still has a problem in the sense that there's going to be a conical singularity on the space-time. But this conical singularity, you can actually remove it. So what you can do is basically, and this is the part that is interesting here that also might make you nervous, but a way that you can remove this conical singularity is by doing a singular diffeomorphism. So it's singular in the sense that I'm going to be doing a diffeomorphism that is linear with the angle. This is not something that we tend to be comfortable doing. It's not the usual type of diffeomorphisms that we do because we like this coordinate to be periodic. But what we showed is that if you do a diffeomorphism where this is linear with the angle, but then times a vector that is a killing vector of SL2, the resulting metric will be of this form. And here in blue, I basically highlighted how the diffeomorphism is affecting the metric, okay? And the SL2 diffeomorphism, because you have an ADS2 that is fibered. So before I told you these are the diffeomorphisms of just the ADS2 part, but because you have a fiber, the diffeomorphisms get also a contribution coming from d phi. And so this SL2 diffeomorphism for neck looks in this way. But again, it has a very nice covariant form in terms of the variables at hand. Okay, so this field chi1 here has to satisfy, it's basically a field that also satisfies the same equation of motion as the previous field. And so with this, what you can do is basically show that you can have both the orange and the blue terms turned on and make sure that the whole solution is completely regular and there's no problems at theta equal to 0 and theta equal to pi. Okay, so this is one of the outcomes. Now,
sorry, and so what is this solution? Is this just what Dan was asking before? Is this just the solution you would get from the order lambda correction from Kerr to neck?
Again, if you pick epsilon equal to lambda,
yeah,
it will be the solution to the decoupling limit. And also if you make it static, like if you don't put any time dependence on it. Of course, because the decoupling limit, the simplest form of the decoupling limit will have, this is a solution. So if I make epsilon equal to lambda, then yes, this will be exactly the solution to the decoupling.
Wait, but otherwise you're telling us that there are further regular propagating axisymmetric solutions of neck.
Yeah, so you would have to say why
exist in Kerr. I mean, what happens to them in terms of Kerr?
Today I don't have anything to tell you about it, but there's nothing here that tells me that epsilon has to be lambda because you forgot about the UV. So this is about how you connect the UV to the IR. So prior to you telling me how you connect the UV to the IR, there's no reason why you should have called epsilon lambda. If you see what I mean. So there would have to be an argument that this has to be like that the only effect it could have possibly had was to be the lambda that you use in the near extremal context.
Is this solution consistent with having another asymptotically neck solution? So if I ask what's the nonlinear completion of this regular linear?
Oh, I don't know. That's a good question. I don't know what is the nonlinear completion to it. But I can tell you that it matches, of course, the one that we know, but that's a very difficult question, because I'll also mention it that there are some, it's because of the throat that things forget. And so when you ask about like, oh, how do you fully reconstruct some things, there's a lot of ambiguities and how you do it. So it could well be that you're forced to, for these type of configurations, to pick epsilon equal to lambda. But from this IR perspective, it's lambda doesn't mean anything in this.
Yeah, what's the problem with just considering a general metric perturbation on this background?
No, then there will look like so. In general, like the general metric perturbation, you have a matching procedure, because I also know what the propagating modes are from infinity. And so that's something that we discuss in the paper as well. So for the propagating modes, it's very clear how you match things from the perspective of the IR and the UV, because I know what's happening far away. And I have the Tolkowski, I have the Weil scalars from the far.
Right, but that's for lambda greater than or equal to 2, for L greater than or equal to 2.
Exactly.
This one is different one. So that's
no,
not
exactly. So, but I know, but here I'm like, I have more ambiguity, right? So for the propagating modes, the story is clear, right? Because you can be, if you're far away, you tell me what are gravitational perturbations, they're this. And then you look at the Tolkowski equation and you see it in the far region and you see it in the near region, and then there's a matching region, and then you glue the solutions and you go in your happy way. These ones, because they were already a little bit weird from the perspective of the interior. So one thing that we showed is basically how you can construct the diffeomorphism. So I'm getting ahead of myself, but there's a way how you can construct the diffeomorphisms on the outside that glue to this. But we can only describe the diffeomorphisms close to the throat, because there's ambiguities on how you quantify the diffeomorphism when you're very far, because you can basically complete it in many different ways, and we don't have a good rule on how you complete that diffeomorphism. So for instance, for some of the modes that I'm not talking about, the L equal to 0, the marginal ones, there's connections with a symmetric that you might think that it's then further connected to like a super rotation. So that there can be something interesting there, and like, oh, how do they connect to some of the deformations that you expect to see on the celestial sphere, let's say, or something like that. So it's the...
Yeah, but just to make sure I don't miss the point. So this metric perturbation, even though the construction of it was weird, it was originally a singular solution, you did a singular differ on it, but the final metric perturbation is completely regular. So there's nothing weird about this as a perturbative axisymmetric, even propagating.
Yeah, but it's how you discover it. So it's like, how do you come about with this? So that's the point. There's and we're very happy that it's regular now. Yeah.
Okay.
But it's basically like, it's like, how do you see that the JT sector is basically having this effect on the line element, right? And what is the origin of the different pieces? Because the parts in orange, what I think is interesting, they come from a different perspective compared to the parts in blue. So there's a balancing here of these two quantities like that gives you some insight about what's happening. And yeah, but okay, I think I'm running short on time. I'm basically 2 minutes away from my cutoff. So because this is part of also the discussions I had. So if I
there's no need to rush. Take your time.
Okay, just okay. But in any case, but I think I did had some of these comments of what Achilles is like grilling me on now. on the next. But let me just summarize a little bit of what's going on here, because I think it's important. So what we had basically, from just in contrast to the case where we had spherical symmetry, what we basically, here I just wrote down the parts that are interesting from this JT sector point of view. But so that's why I have like a bunch of dots. I'm not writing down the full line element. But basically, when you move upwards in this direction, you basically get these two contributions that match together, are regular, and they basically come from demanding that the bioscalars are fine, zero, and this large diffeomorphism. Now, what I should say is, as was discussed, there's no curvature singularities, there's no conical singularities in this JT sector. And also something that we did to show that they were physical as well, because you might be like, great, you canceled everything, but this might still be like something very trivial that carries no information. Something that you can do from the point of view of this background is to compute the Iyer-Wald charges of the combination of the blue and the orange. This actually gives you a finite Iyer-Wald charge. So you get 3 of them for each of the 3 killing vectors that you have. But if you were to compute the Iyer-Wald charge associated to just one of them, you would have actually got something that didn't make sense. Basically, it's not conserved, or it's either singular. So the combination of the 2 of them is actually what gives you a finite number. So at least in the perspective of when you're sitting here, there's an observable that cares about these modes, and it's basically these Iyer-Wald charges that you can compute. So they carry a finite Iyer-Wald charge, which is very nice. Now, the thing that, and this is what we were talking about, is like, okay, great, but I want to go from the top to the bottom, right? So the discussion that we were just having a moment ago is like, what does it mean from this perspective? And so in our paper, what we did discuss, well, we discussed it for the propagating modes, and we also discussed it for this modes. And so one thing that you can see if you make the right choices is that, as it's been asked a few times, you can see that these deformations induce a change in mass. That you can make the gluing very precise. And it matches like your intuition from the decoupling limit, even when you go a little bit away from extremality. And we also showed how you can build diffeomorphisms that smoothly interpolate down to these functions. So in the limit that lambda goes to 0, you can see there is, because they, in some sense, they had to be diffeomorphisms since the bioscalars vanished. But the problem with that construction, the thing that, and you will see commented in the paper, is that we can constrain the diffeomorphism near the throat, but there's nothing that constrains the diffeomorphisms basically up here. So there's an ambiguity. From our perspective, it wasn't clear what to say about how the diffeomorphism looks far away. We could only say how the diffeomorphism looks. So you start from here, but then we can only say things about how the diffeomorphism looks near the throat again. And so what I don't have for you today, and it's one of my open questions, is that I don't know how the diffeomorphism looks from this perspective, and then say, it also is physical from the perspective of far away, and you should associate as well. If it had an Iyer-Wald charge in the throat, there will be an associated Iyer-Wald charge at infinity. That I don't know the question to, but I find it an interesting question to keep track of. Okay, so let's conclude, since time is running up. So what I did today, I'm basically, like, the punchline at the bottom end is that there is a universal, many of the universal aspects that you think happen in rotating black holes, they also happen in the Kerr geometry. So this JT sector is present there. And so from that point of view, if you think of it as building an effective field theory, there's a corner of this effective field theory that is very, very similar to the Rice-Nostrum black hole. The thing that is interesting, it's just like, in some way, there's this mechanism of like, how do you realize that this mode exists in the geometry? Because again, if you just did the Tolkowski formalism, it's very easy to miss them because you would have said, I only want well-supported solutions. And the other thing to say that it was kind of illuminating for me is how much the angles played a role in the whole construction. So in the Rice and Ostrom, you don't have to think about angles because you just have the sphere. And so there's nothing like, who cares that there's a theta and a phi? But in the Kerr solution, the whole mechanism relied quite a lot on the fact of what is happening on the S2, and that you allowed for moments of your time to have singularities on the sphere, and then remove them if you wish. You can also think about keeping them. So I actually think that it might be interesting to let the singularities live. And so maybe if you don't want the solution to be regular, to just say, hey, keep the singular mode on the sphere and just see what happens. So why would you have to balance, in the context of what I was saying of the Weil scalar condition, you can have said, let me just do that and still have some singularity on the sphere. How would that map in the far part? So yeah. Given that in other contexts, we are also allowing for singularities on the S2, this might be something useful and interesting to say. So with that, what is next? So here are some, in this context of Kerr and Neck, there's some things that you can say here. So noticing that this does a change in the mass of the black hole. It's not difficult to see, but it's in some sense you do want a little bit more than that. So you do have this whole Schwarzschild effective action from the point of view of the interior. So you might want to have a better understanding of what that looked like from the perspective of the UV, so from the far region. And then more in a GR, in other realms of black hole phenomena, you might want to connect this JT sector to if it has some interesting interplay with superradiance, if it has an interesting interplay with love numbers, how can you say something about the appearance of this JT sector and its and the responses of black holes in other contexts. And also something that is also discussed in more of the mathematical literature. When you think of black holes, you also think about their Arrakis instability. Which is the way that you think that extremal black holes are unstable because anything basically, the solutions basically blow up in some way. And it will be nice to understand from this perspective of ADS-CFT of how those instabilities kind of come into play with this deviation away from extremality that we're describing in the JT sector. So that might be fun to think about more carefully. Now, as I was saying, I'm not shy of having just the singular perturbations by themselves. So you can decide that you're comfortable with having pathologies at 0 and pi. And I do think that there's something interesting to say in that context. So the deformations that correspond to the symmetric deformations will be nice to study. It would also be nice to understand why this making sense of this effective theory of ADS2 you had to say things on the sphere that I don't know, if you have a very ADS-CFT perspective, the sphere usually plays absolutely no role. So that's kind of curious. And also another thing that is interesting to say that if you allow these singular perturbations to exist, from the point of view of the Hertz potential, which is the object that you use to usually reconstruct the metric on different portions of the geometry, these singular perturbations have a non-separable Hertz potential. So it's also kind of from a mathematical perspective, it's interesting and challenging to understand how will you do gluing of solutions that are non-separable in this context. So they're non-separable in the context of the RT, the ADS2 coordinates. So the angular part always separates, but you won't do a Fourier mode decomposition of these solutions. So how will you go about gluing solutions where the radial and the time component are not necessarily friendly to having separable ansatz? So that, yeah, there are singular perturbations, so then you might not like them for that point of view, but I think conceptually it was an interesting thing to play around with. And then finally, I had an extra slide to also tell you about what are other things happening in the context of near extremal black holes that we have been investigating that are not related necessarily to Kerr. So I just had here, for instance, so here we were talking about black holes in ADS2, sorry, in Minkowski and roughly in ADS4, but there's also something a lot of fun to say about black holes in de Sitter, for which Chiara can tell you more about. That also, again, there's different behaviors and different patterns with Evita as well. If you embed these black holes in theories that are supersymmetric, there's also the spectrum of deformations is much more rich. And so JT is not always the thing that is towards the bottom. And then if you care more about like Kerr CFT like things and like and how some of these rules happen in contexts where you have like these warped type black holes, we've been working on this, and this is more formal on the quantum side. But in any case, I'm out of time, so let me just end with a big thank you, and thank you for listening and holding up with me. So I'm done.
Okay, let's all thank Alejandra for a very clear, very interesting talk. And we have time for questions, so just unmute yourself.
Yeah, I have maybe a bit of a, technical question, because I was familiar with your paper with Victor, the previous paper that you had, the perturbations. So there, it seems that you find two modes with delta equals 2, right? One was the JT mode and the other one was another one. I mean, I guess that the analysis is different.
So in that case, oh, sorry. Go ahead.
I guess that the analysis was a bit different because there, the perturbations, I think, were depending only on RNT. But is there any way that, I mean, how these two analyses are related?
It's basically, so this is an improvement on that analysis. So there we did basically what Dan was suggesting initially, like, try to guess what's going on by looking at the decoupling limit.
Yes. Mm-hmm.
And so it basically gave us some form of the combination of the orange and the blue. That's the only difference. But these guys, so just to be clear, let me just show you, let me see which equation is the most clear. So this chi JT, in some sense, it doesn't have angular dependence because here you have a sine squared and a 1 over sine squared. And so what shows up in the metric is just this chi 1. Okay. So that's why it looks basically very similar to what we wrote in the first paper that we had with Victor.
But there you had two fields with delta equals 2. They are combining their.
Yeah, exactly. So then so basically, so it was the blue and again, it's a version of the blue and the orange, because we didn't notice that they were actually one and the same, that you had actually a conical singularity and you had to match them to really say, there was only just one.
Okay. So eventually it was just one with delta equals 2.
So in that paper, we were basically treating both of them like separately.
Separate. Okay.
Because the equations of motions didn't tell us that they had to be the same. And so something that we overlooked was the fact that if you keep them like completely different, then you do have a conical singularity.
Okay.
If you make them the same, then it's fine. So, but it was based on a guess. So we were like, doing the decoupling limit, seeing what the first terms were, like where did they show up in the metric, and then we thought like, this is probably a good ansatz for how the deformation looks like. But then here it really comes, we liked more, that's why I was pushing more this analysis, because it's a little bit more systematic in order to say like, okay, this is how you do it carefully, and you see what is independent versus dependent, and what is their origin in some sense from a more
starting from the IR. I mean, only starting from the IR without asking necessarily a decoupling limit from the UV.
Exactly. So we're not in this context, we're not asking it as a decoupling limit. Originally, when we did it with Victor, we asked it for a decoupling limit, and then we were making as well, like, okay, we think that this is how you should describe it. But at the end, like the important correction is that you do have to make these two equal to each other.
Okay, very good. Thanks.
Yeah. So we had them as separate, but you actually have to make them equal.
Alejandra, why don't you also find a diffs1 zero mode in the spectrum? I would have thought that you could just do one of these diffs, which is
Oh, I'm just ignoring it. That's why everything is covariant. So everything that I'm writing, so those will be diffeomorphisms on here.
they don't touch theta and phi.
No, they don't touch. Oh, well, in a way that it's like it will be plus a gauge transformation in A. So your diffs, so that's why we wrote everything covariantly. So if you wanted to turn on those modes and be like near neck, you can do it easily in this formalism because it just means pick the coordinates where those diffeomorphisms are manifest.
Okay, but that zero mode is the one that you expect to reproduce Schwartz and stuff and give you the.
Yeah, but it's in the combination with it. So let me just go back to the JT action. Yeah, but for those modes to have life, so those modes are basically, you would say, yeah, they're just reparametrizations of your ADS2 geometry, or well, in this case, in combination with the gauge transformation and phi. But those modes are only meaningful, or at least the story that it's told is that they're only meaningful if you also have the Y turn on. So you can say that they account for the entropy near extremality if this guy is sitting right in front of them. Because their action, otherwise, if you compute their effective action, so let's say that you have a model of 2D gravity without the Y here, or if the Y is constant, so let's say you just put it to constant, then you would compute the action for those modes and it will be 0. So that's why it's important to find this delta equal to 2 mode, such that those extra things, those diff S1 actually become meaningful. And then it's meaningful for them to also glue to infinity. So
let me see. So are you saying if I turn on this particular perturbation that you've identified, and now I go and try and compute the one loop determinant, now those diff S1s will have finite action, which I can.
Yeah, exactly.
Okay.
Yeah. So the computations, for instance, there's these computations by Turiachi, Ileshu, Hayden. Sorry, I'm probably some of them. I don't know who's connected, but okay, there's many people working on this, and so when they compute the log corrections in that context, this is from the point of view of the IR, this is the action that they're using, and so those modes contribute to the log T because you can claim that this is the effective action for them.
Yeah, and in particular that there's a background field for Y.
Yeah, so this Y is basically a linear dilaton type field.
Okay, so if I want to do their calculation in Kerr, I just need to take the solutions for that field that you found in NEC, turn it on, compute the determinant.
Well, you can even do something dumber, like because it depends on like how careful, like what does this look like as doing a solution? Doing a computation. But I think if you just wanted like the sort of like quick answer, I basically just told you there's going to be some complicated effective action for Kerr, but this will be part of the pieces in the game. And if you just want to know what the first response in T is basically going to look like whatever this gives you. So there's, in some sense, yeah, there's nothing to.
Well, that'll give the linear in T.
Yeah.
Right,
yeah.
but
if you
I
wanted
want
something
the logarithmic.
No. This also has the log. So the log comes from here as well.
Is that right?
Yeah. So the Schwarzschild effective action has it's basically beta to the 3/2 times e to the pi squared over beta. So what you're thinking is the exponential part that has the linear response and temperature, but then you have 3 zero modes coming from each SL2. And that gives you the beta to the 3/2, which is the generic log correction that you get. So, and that all comes from quantizing the boundary action that comes from JT gravity.
Mm-hmm.
So wait, these 3 zero modes come from where, sorry?
The SL2, that you have
okay, so
3 isometries from SL2, basically. That's how people usually interpret it, that you got beta to the 3/2, because there's 3. It's just that it's also why the killing vectors of SL2 match with the 3 solutions to Y in some sense, that it's basically 3 zero modes of SL2. Yeah, it's because the theory has the Schwarzschild action is invariant under SL2 transformations.
Yes.
And so then those, if you do a path integral of that theory, then you will get these 3 zero modes as basically exact symmetries of that action. So that's why you get 3 halves.
Can I ask one more question? So if I take the large differs of ADS2 and I act with them on the order lambda correction that you get from Kerr to neck, will I get all of your regular blue plus orange solutions?
Sorry, so you want to act. So
there is an order lambda, there's one linear solution around neck, which comes from expanding extreme Kerr around neck.
Yeah.
And then there is a large difference of ADS2, which I can use to transform that solution to other things, other solutions.
Yeah, it will all come because it's covariant. Yeah. Unless, yeah, everything in the formalism is covariant. So if you decide to change your coordinate systems in ADS2, then it will act on everything, because all the equations that I'm writing are basically, oh, you will resolve the field in that coordinate system. And so
right, no, but I'm asking a different question. So yeah, if you transform both background and perturbation, what I'm trying to ask is it perhaps the case that all of your regular, I'm still puzzled about what the regular solutions around neck that you found are. And a guess would be that maybe all they are these differs acting on the one good solution that we know should have been there, which is that that first order deviation away from neck.
Again, we did show that if you pick epsilon equal to lambda, they will become that, but you don't have to pick epsilon equal to lambda.
But they will all become just that? I thought you had plenty
well,
of
up
solutions
to like there's always so. Okay, so let's be clear a bit, because when you do the decoupling limit, in the near extremal case, the only thing that you see is the increase of the mass itself, right?
Yes.
And so that, technically speaking, is only one of the configurations from this perspective. It's not all 3 of the configurations. So I'm putting it in the language of like that you have 3 orbits for these solutions, right?
You're
like
talking
you have
about
3
orbits now.
Oh, well, 2 orbits, okay, but sorry, let me just talk about it in the sense that, yeah, so in this solution, yeah, you have 3 integration constants, and each of them give you a different like SL2 charge that you can turn on, okay?
Good.
So
yeah.
One of them is the one that you naturally associate, and then, yeah, you can write in terms of this Casimir, and you can naturally associate it with like, okay, this is the thing that gives you an increase of mass. That one is, yes, that's here. There's no ambiguity on that being here. Then if you wanted to look at the other 2 SL2 modes, then we showed that there is a diffeomorphism that will smoothly go into the interior and give you those other 2 SL2 modes, okay? But another thing that we were discussing is that there's a sense in which you can also do deformations that perhaps, it depends on how you deform things at infinity, but again, you don't have to do it in a way in which epsilon is related to lambda. That's part of the point. And in particular, from this perspective, there's no need to say that epsilon was equal to lambda. But everything, at least for my understanding, so that's why I was not quite sure if there's everything that I was expecting from a decoupling limit perspective is going to be captured by this. I don't think I'm missing something, but I'm pretty sure I'm not missing.
But you found plenty more solutions on neck. And
yeah.
I'm trying to force you to make a guess, I suppose, on what the
it would be difficult. You will not make me guess, because I with Wei and like, oh my God, I'm not going to make a guess. We really wanted to understand can we say
Okay.
something more? Like we spent, this was some pandemic years where we spent many hours on Zoom, and I decided, and we both decided, like, you know what, this is what we can say very carefully and clearly, and we hope that, yeah, I think it will be super interesting to, like, even if you wanted to discard them, I think it will be fantastic if you tell me, like, hey, you know, this was all perfectly fine and pretty from the point of view of the IR, but you know what, if you start reconstructing the geometry, this thing is crap, and throw them out. That will be fantastic to know, like, how does that look like? What is the argument? We couldn't find a reason why you should throw them out. Besides, like, the only thing, well, if you actually make them singular and you have the poles at either 0 or pi, then you can say, okay, it's a relativist, like, no, I don't want singularities on the sphere. But I think, I don't know, in the spirit of celestial holography, I might be more friendly to, like, allow for things to be singular on the sphere from time to time. And so there might be something interesting there, and like, how do they look like from infinity? And that might give you more control on what it means to glue them, because then you can also understand a bit better what is how they live in the UV and what it means to bring them down in a way, in a control way. But we couldn't make that statement precise. So that's why I'm going to, there's more things to do. And at this stage, I don't have a good intuition on what's the truth here in some sense, or what should be more true.
Okay, yeah, thanks.
So maybe I can stop sharing.
Yeah, okay. Well, if there are no more questions, let's thank Alejandra again. That was very interesting. I'll stop the recording.
I don't